and we will need to move to session 4. So theme 4, this is our next session. We have conveners from Italy, Indonesia, and Germany, panelists from Italy, Switzerland, and Taiwan, and they are going to be talking about remote observation, monitoring of natural hazards, forecasting, and response. And they're going to start talking about how effectively using expanded remote sensing can be used in natural hazard science. So I'm going to take away the poll here and hand over to Paolo, who will be the main convener of this session. So Paolo, if you'd like to come on board.
Thank you, Alan, thank you. Okay, good morning to everyone. A very quick presentation about myself. I'm Paolo Taroli from the University of Padua. My topic is digital terrain analysis using high-resolution topography from remote sensing. And I'm chairing the session with other co-conveners who I will ask to present themselves. One is Gayatri, please present yourself.
Hi everyone, good morning. My name is Gayatri Mulyani. I'm assistant professor at Universitas Gadjah Mada in Indonesia. I'm mostly working on earthquake geology, tectonic, active tectonic. So I'm mostly using paleoseismological approach and rapid assessment after earthquake happens. So nice to meet you all. Thanks.
Okay, the third convener is Niels Hovius.
Hi, good day everyone. I'm Niels Hovius. I'm based at the German Center for Geoscience Research in Potsdam. I'm interested in many erosion processes. There are links to tectonics and to climate. I have long studied landslides.
Okay, thank you. Let's move to the panelists and the topic today. I will present very quickly the topic, and then I will try to introduce each of the invited speaker. So, in the last decade, a range of new remote sensing techniques has provided new opportunities for a better understanding of Earth surface processes. And if we look at the literature review, the number of scientific studies that considers application of remote sensing for the management of natural hazard effect, the identification of occurred damages, and also forecast strongly increase in the last decade. And the purpose of this question, of this session, is to provide an overlook over 3 different kinds of remote sensing technique that they have two different kinds of scale, a spatial scale and a temporal scale. We invited 3 speakers. One is Daniele Jordan, the other one is Fabian Walter, and Yuen Ain Liu. Please present, each of you, give a short presentation about yourself and your topic, and then I will leave you 5 minutes talk. Daniele?
I have to start, okay, so I'm Daniele Jordan, I'm a scientific researcher. I work in Italy in the National Research Country and in particular in the Research Institute for Geohydrological Protection. We work on landslide monitoring mainly, but we are working on the development of monitoring system for many geohydrological instabilities. That means also the monitoring of glacier and also of flood effects over large areas. My topic will be focused in particular on UAV, unmanned aerial vehicles.
Great. Fabian, please introduce yourself quickly.
Hello, my name is Fabian Walter. I am an assistant professor at ETH Zurich. I study mostly glaciological processes, glacier dynamics, iceberg calving, glacial break-off events, and in the last 5 to 6 years, I've also started looking at alpine mass movements. And I'm particularly interested in seismological and infrasound measurements of mass movement. So the context of remote sensing for me is not satellites or unmanned autonomous vehicles, or not primarily, but I'm looking at seismic data which are remotely describing the mass movements of alpine masses on the Earth's surface.
Great. Let's move to the third panelist, who is Yuen An Liu. Please introduce yourself.
Hello, everyone. This is Yuen Liu from Taiwan, and I am interested in the use of remote sensing data and GIS technique for environmental research and also our typhoon research. And today I would talk about the outcomes of our typhoon research primarily.
Okay, thank you so much. So let's start with the first speaker. Daniele, please share your screen and try to bring your presentation into 5 minutes. Yeah, sorry, your microphone.
Sorry, okay. Can you hear me? Great.
Please.
So it's quite hard to describe a managerial system in 5 minutes, but I will try to do it. You know, these systems have been characterized by a strong development in the last decades, and nowadays are widely used in the management of natural hazards. You know that UAV are cheap and easy system, are able to fly automatically over our area of interest and acquire a sequence of image or other data. And in particular, if we consider natural hazard, one of the most important points in the UAV is the possibility to carry some payload and fly over dangerous area, avoiding risk for operators. We know that actually the number of possible payloads are increasing. We have an incredible number of possible cameras that we adopt for this system. And nowadays, also LiDAR and multispectral cameras starting to be important possibilities for this system and this application. But an essential element that supporting the diffusion of the UAV is, of course, tracking from motion. This computer graphic application can generate ultra-detailed 3D models of the area interest from a sequence of images. Probably you know very well this method. And of course, the number of possible applications in the field of natural hazard response is incredibly high because UAV and certain from motion give us the possibility of the acquisition of accurate representation on dangerous areas. This is only an example. We can acquire a 3D model of and obtain a digital outcrop, and starting from this model to identify joints and also the critical combination of joints that can cause rock falls. But if the question is how we can effectively use these expanded remote sensing approaches, we can consider that in the field of UAV, we have two different ways of development, technological one and methodological. One of the most interesting technological development now is indoor underground autonomous flying. So the possibility of using this system not only outdoor, but even indoor. And from the methodological point of view, I believe that one of the most effective improvement that we have to consider is the increase the possibility to have a real multi-scale approach. This is only an example. If you have to define the effect of a flood, of course, you can start from satellite images, and using this satellite image, you have the possibility to define the area, the flooded area, but then moving to a different scale, you can start to use aerial or high level UAV and obtain this first detailed representation that can be used for a detailed mapping, but also, as in this case, for a 3D model that can help to define the level of the water. Of course, when you have some important elements like a levee and a levee breaching, like in this case, the use of UAV can be a very, very good solution, because you have the possibility to create a 3D model to define the level of the effect of the floods and also the occurred damages. The problem is that when we started to work inside the city, the use of aerial image can be a critical point, because we have a NatHazards approach, but not always the NatHazards approach and this use of this image can be the right solution. That is why if we combine, like in this case, also terrestrial image, we can create, for example, 3D model of facade of buildings, and also measure the level of water that flooded in this area, and obtain in this way a more detailed evaluation of damages. Thank you for your attention.
Thank you, Daniele. Very good. Let's move to the second speaker, Fabian, please.
Okay, you should see my screen in the next moment.
Yes.
Okay, waiting for the full screen. There we go. Okay, thank you. I will talk today about methods to warn against the debris flow hazard. And I'm starting with this image right here, taken from 30 kilometers above the Earth, that's showing Switzerland and the French Alps right here. We have lots of debris flow hazards, hundreds of debris flow events in these mountains every year. And I will focus actually on this small canyon in the lower right corner, which is our natural laboratory. So this is it right here, the EGU catchment in southern Switzerland. The Rhone Valley, which you may be familiar with, runs right here. The Rhone runs towards the top left, top right corner. And the EGU is a very active canyon that produces a lot of erosion at the lateral slopes, which then accumulate in the torrent right here. And when there's heavy precipitation, these sediments are then evacuated in forms of debris flows. And we see actually more and more of these. This year, there were altogether 13 debris flows. I'm showing you a video of one event right here, a nice example. These are not really destructive events anymore, because there have been a lot of measures against them. And this includes an early warning system down here on the lower part of the torrent, which consists of flow depth measurements and geophones installed in these check dams. And so these detections are actually quite reliable. We do not have warning points up here higher in the catchment, because there we cannot put anything into the torrent. And that's where the idea of remote sensing comes in. We are now in the 4th year of placing seismometers all around the canyon. Right here, you see the seismic data down here. And with these, we're hoping to detect the seismic waves emitted by the debris flows. And the sensors are rather portable. You see right here, they mostly consist of a large solar panel, a box with a digitizer, and a sensor buried in the ground. Now, we've spent several years trying to build threshold combinations that warn us in real time for debris flows, so to catch them as soon as they happen. And although sometimes this works, the problem is that if we simply use thresholds, then we have too many false alarms. So, and too many, I really tell you, it's unpermissible, and we have hundreds or even thousands of false alarms. So then we move from the idea of simple thresholds to using a machine learning approach. And I won't go into the details here, but just to tell you, we're translating seismic signals such as this one into features. That this could be the maximum amplitude, it could be the Fourier, the maximum Fourier spectrum, or rise and fall time whatsoever. And we now have a large number of events, so we can train such a machine learning algorithm with 20 past events. And again, I won't go into the details, just that we're, instead of trying to define thresholds, we're telling the computer how to define a complicated set of thresholds itself so it can take decisions. And so we tested this first of all on the 2017 data. This is what I'm showing you right here. On the vertical, the Julian day, on the horizontal, the time of the day, and we're continuously classifying the signals into noise, which is the light pinks color right here. So we mostly have noise as expected, and then two debris flow signals. One would be the signal emitted by the mobilization in the higher catchment, the blue points right here, and then the green signal as the debris flow moves further down. And you can see that we actually seem to catch the debris flows quite nicely in early mobilization phase, followed by the propagation phase. And we tested this in real time in 2020 in this year, and recognized correctly all 12 larger events. We had no false detections, and some of the early warning times go up to 2 hours. So between the nucleation of the debris flow and the arrival down there at the cantonal road, 2 hours. So an outlook, I think with this machine learning approach, we can combine many more time series, such as infrasound. And in general, seismology and infrasound are a big data type of record. We see, for example, for the IRIS data set, how much this volume and data has been growing. And also in Switzerland, we have plenty of seismometers permanently streaming data, which we could use for such an approach. Now, finally, I want to say that there's a new development in seismology. We can now actually also use fiber optic cables rather than seismology, seismometers to detect seismic events. And with this, we would have an everlasting increase of seismic sensors. And I'm showing you the network coverage as an example for Switzerland. Thank you.
Thank you, Fabian. Very interesting. Let's move to the third speaker, that we are changing totally the technique and also the scale. Please open your microphone.
Okay, yes.
Okay, great. You can share your screen.
Share my screen. And okay, so can you see?
Yeah. Please.
Oh, so I start now?
Yeah.
Okay. So thanks, Paulo, and good afternoon to everyone. Here is in Taiwan, it's afternoon now. What I'm going to present is totally different from the content of previous speakers. As I said, I'm going to present our typhoon research outcome. And so the topic is about the observed increasing super typhoons in the Northwest Pacific Basin in recent decades. Here is the impact of the change in the number or frequency of typhoons that attacked Taiwan. In the past, Taiwan is attacked by typhoon quite frequently, generally 2 or 3 typhoons at least in a year. But this year, so far, we do not have any typhoons landfall so far. So that up to this point, the water storage of the reservoirs in Taiwan reaches the lowest level in the recent 70 years, as shown in the diagram. And this storage is below the average by 30%. And this is a very abnormal situation. From the next page, you will see. This is what happened due to the impact of the typhoons in Taiwan. And nowadays, recently in Asia, not only Taiwan, but also in the northern latitude countries like Japan, Korea, North Korea, have been attacked by the typhoons quite seriously. Not only in Asia, but also in USA. Just in last month, 2 typhoons occurred in Mexico, Gulf Mexico. And this is very unusual situation. So the typhoon or cyclone, hurricanes, this extreme weather cause a lot of damages to the society in different parts of the world. And then why the current typhoon behavior differs from the past? And we analyze the typhoon data for the past 40 years and acquire some finding as I'm going to share with you now. So here shows that every year Taiwan suffers a lot of damage of properties with some numbers of losses of life due to heavy rain, landslides, frost, tree falling, and the big economic losses by the attacks of strong typhoons. And this type of issues was also mentioned in the previous session today. And the cause behind these all losses is in that the country falls in the region of the Northwest Pacific Ocean, as shown in this figure. 1/3 of the whole world's typhoons take birth every year, and so this is which is so far the maximum in the whole world. So that in this region, like Taiwan, ranks number 7 in the list of countries which receive max number of typhoons every year since 1970. And this page shows that the increased super typhoon that occur in this region. So from the diagram, we have on the right, in the middle, we have a single super typhoon or double super typhoon or even triple super typhoon, either in the summer or in winter time. Overall, we can see that the frequency of a super typhoon is increased in recent years. So this is based on the data set that we analyze. So the stronger typhoons, the more in the number in recent years than earlier. And these strong typhoons survive for a longer time, and cause very heavy damages. Also, the number of the cases between typhoons, also called the Fujiwara effect, is increased. And based on our analysis, we found that the enhancement of the typhoon could be due to 2 major factors. One is the interaction with the southwest air flows. or the northwest cold air masses. And these two weather phenomenon occur primarily in summer and winter, and they would enhance the typhoon to become super typhoons in summer and winter respectively. And this is a very important finding in our research. And this shows the track analysis of a typhoon in the North Pacific. On the left panel, we show that the overall spatio-temporal typhoons track, and based on the 40 years data. And on the right side corner, bottom corner, you can see the different type of tracks. The figure A shows the straight track typhoons, and then B, the quasi straight tracks, and then C is a quasi sinuous tracks, and the D figure shows that the sinuous tracks, and each the different tracks of a typhoon would lead the typhoon to different regions or countries, and then would cause different impacts through on the regions where the typhoon passed by. So based on the tracks, we would be able to know that which countries would be affected by the typhoon, and the trend of the typhoons, how the typhoons influence the different parts of the of the country in these areas. And so based on that, we give a brief summary about this analysis. Strong enhancement of storm track seniority is observed as we move early to late typhoon season month. That is from the month of July to October. And the number 2 point.
You have
yes.
1 minute, less than 1 minute, please.
Okay. Okay. So you might you can read this the writing quickly. Okay. Then I move on. And I will skip this. This is a very important formula that we developed to define how two typhoons would interact with each other. And the results are presented in the paper. And also we studied the impact of typhoon on the urban green space. This is a framework that used. And we analyze how the typhoon impact at different regions and the level, how the vulnerability of the region to typhoon. So we primarily use easy, accessible, and free of charge data set of acquired from the satellite, and outcomes can be very useful not only to the private researchers but also to the government. Okay, and our research outcomes are acquire attention from AOGS-EGU EOS, and in August, 2 reports are based on our research findings about the typhoon, and the links are given below. If anyone is interested, you're very welcome to read the report. And this page shows the references about the typhoon published in the recent years. Thank you.
Okay, thank you so much. Thank you so much for your presentation. Now we have time for open discussion. Before starting the open discussion, I would like to highlight to you and to all the attendees the possibility to join our Padlet. Already Bruce posted the Padlet link we set it up, so you can go there, download the presentation. The free presentation are already there. Okay, I would like to start with one question, and then I will give to Gayatri other question opportunity. In this short sequence of presentation, we saw three different kind of remote sensing approach. Low cost local scale, very sophisticated local scale, and then large scale analysis. So two are the scale, spatial and temporal scale. And of course, remote sensing techniques are different. The question is how we can better integrate different remote sensing technique into a framework for natural hazard forecasting and response. I would like to give this answer, open this answer to each of you. So feel free to answer and to raise the challenges in integrating this different technique into one single framework. Okay, you are free to reply. Daniele, Fabian, Yohei, please.
I will try to start, and then I hope that the other convener will follow my simple example. Yeah, so I believe that this is one of the most interesting questions that concern our session. The problem is that we have an incredible amount of example of study done at different scale. But according to my experience, one of the problems is that if we consider then study that use a multi-scale approach, the number of paper, the number of publication is quite inferior. We have several examples of people that try and succeed in this approach. Also, I have my experience in this approach, but I believe that on one hand, there is the results that is published on paper. On the other hand, there is a real application over a large area that require, according to my experience, a different organization and a different structure. So what probably is missing now is a structure at national or regional scale, it depends, that is able to acquire, to manage these different data. Of course, in Europe, we have programs like Copernicus or other programs that usually work with remote sensing, with satellite images, but systems that are able to manage both satellite and very local scale images and very local scale data, like, for example, UAV or other system, well, are not so present on our territory, and I believe not even in different other countries. So probably this is the point.
Okay, Fabian, maybe your point of view on this?
Well, I think the big challenge is also the data aggregation. Collecting all the data wherever it comes from in real time, making it available for an analysis, and then also to have the processing capabilities to process all of this in parallel and in real time. I think this is a big challenge. We see very often after something happens, okay, there was a sign here, we could have done this, if we had a sensor right here, and I think actually we're being flooded with data, and a lot of it could really be harnessed or leveraged if we had a way to process these things in real time with the right algorithm.
Great. Yoann, and you have also your view on this?
Hello?
Yeah.
Okay. I think data acquisition for different purposes would be very crucial, and to acquire the data that is suitable for different kinds of environmental issues, that would be a big, quite challenging. We need different different scale or resolution data for different disaster or events. So I think how we can acquire the proper data would be a very challenge issue that we need to conquer, and so that we would be in time to resolve the challenge that we are going to face. Okay, thank you.
Thank you, thank you. Gayatri, if you have some questions to raise, please.
Yeah, I think following up to the previous discussion about data integration, I think the next question will be applied to each of you. So the that the equipment pool with expert are needed for rapid deployment during a crisis. So what do you think? Like for example, if you want to fly UAV and install geophysical instrument, how should this be coordinated? Because as you know, that the hazard may not follow country boundaries. It can affect many physical and administration boundaries. And so what do you think in the future or now that this should be coordinated among the scientists itself? So please, three of you, if you could, Fabian first, and then Danielle and you. Quick, because we have such limited time. Thanks.
Okay, I think the infrastructure for the data acquisition has to exist always, and then the deployment has to be. It could be even an autonomous drone or very low cost sensors, but the actual deployment should not be the critical factor. It's when we have it deployed and anyone could do this, anyone who has received some training, then the data needs to flow immediately. And so I think these data structures, they need to be prepared before a crisis.
All right. Danielle, any thoughts?
No, probably it's not.
Oh, okay. You, maybe you want to take
some
ahead.
problem on connection, so I missed the last few minutes. Sorry.
Got it. You, if you could take on.
Me?
Yes, please.
Okay. I think we need to have a very good infrastructure that is capable of dealing with the data acquisition, processing, analysis, and given that whatever data we are able to obtain, then we would be able to handle the data and then provide the added value to the data we acquire. Actually, our center, my center is the Center for Space and Remote Sensing Research, and we are receiving station. We have our receiving station, and we receive different kinds of satellite data, and we develop our own acquisition software package, and also the processing, and our researchers have expertise different, so that we would be able to kind of provide a total solution to the challenge, so that from the data acquisition, data analysis, processing, and provide the strategy suggestion. So this we can do it like provide a total solution to conquer some kind of a problem. Yeah.
Okay, we have time for another short question, and then we can summarize because I think we reach the end of the session. So Gayatri, please, if you have another general question to raise.
Yeah, I don't know if Danielle wants to take on the previous question. I already, if you missed the question, I already sent you through chat privately, but if you're not, we can go up to another question. Danielle, do you want to answer the first one?
Yeah, if the question, sorry, I'm ready. So if the question is the combination of geophysical instrument and UAV during emergency, this could be, of course, an interesting point. There is a problem. The problem is that when we work in near real time, as Professor Walter do, and also as I do in monitoring of landside, for example. So the near real time is a strategy that require high frequency acquisition and strong infrastructure that is able to acquire an incredible and manage an incredible amount of data, because the final goal is very often an early warning procedure, so the activation of warnings. On the other side, if we work with remote sensing, that means from satellite to aerial to UAV data, very often these data are acquired on demand, so the frequency of the acquisition, even with UAV, is different with respect to the frequency of near real-time acquisition. That means that, in my experience, so the strategy could be different. On one side, you have the possibility to work on near real-time or in real-time, and on the other side, the use of remote sensing system, that means from satellite to UAV, give the possibility to change the scale of the application, change the scale of the analysis, and improve the possibility to work over large area. So the combination of these two possibilities make, in my opinion, the way to obtain a very detailed description of what happened during a natural hazard, even on a large area. But again, we need a strong infrastructure, and we need also a system that is able to acquire and process all these large amount of data.
Thank you, Daniele. Thank you, Gayatri. Before leaving the window to Adam for the final conclusion, I would like to stress again that we have a Padlet open. I will share to you the Padlet, and Bruce already indicated this in the open chat. Please check. You can download the presentation there. And let me say a few words just before closing the session. That will be, of course, a few words also for the meeting of the next year. After the discussion and the pre-presentation, a few challenges were highlighted for the future. So we need to move into versus those directions. So integrate multi-platform remote sensing into a single framework, data aggregation in real time, process capability in parallel and in real time. So find solution to manage big data in real time, and then data acquisition for different environmental conditions. So try to adapt the best framework, the best solution for a certain environmental condition. Okay, thank you so much. So I will leave the word to Adam, and thank you for organizing this meeting.
Thank you, Paulo, and thank you everybody for being involved. Once again, just make sure you check out the Padlet. The Padlet is a very cool, novel way of having a discussion, and it will stay open for a while. Question and answers, people have answered most of those already. We'll call it to a close very quickly. We've learned a lot today for the 2021 meeting when we'll be in Yogyakarta in Indonesia. Please join us tomorrow. Tomorrow we have 2 more sessions that are on communication and warning systems, and something very novel. There will be an artist joining us who will be doing live sketches of the session, which will leave a legacy for us to all look at. And so something a little bit different for the final day of the conference, but please do join us. It's been a pleasure having everybody here. Thank you very much to the panelists of each of the panels. It's really been a great afternoon, evening or morning, depending on where you are. We're at 5:31, a little over time. So with that, thank you very much. We'll close it for today, and hopefully we'll see everyone back tomorrow for some more fruitful discussions. Thank you.
Thank you.